So thank you very much. Yeah, as Amandine just mentioned, that I couldn't make it because I got COVID a few weeks ago, so I missed out on lots of the fun. But I will say, as someone who's been attending all the sessions online, I've really enjoyed the presentation. I mean, all the different presentations, and thank you to the organisers for that. And I also want to particularly thank somebody. You might not be realising it, those of you in the room. There is clearly somebody who is involved in, the audio visual for the online experience and moving a camera around and making sure that it all makes sense. So I want to say a special thank you to them and whoever that is. And finally, because I can't be there, I wanted to firstly highlight my email address. And, obviously can't experience being in Paris, but would love to interact with you. I know Amandine mentioned that's important. So if you want to, please, connect with me or maybe reconnect with me, just a brief email on any topic of this or just for no particular reason. I really do mean it when I say just please get in touch. So thank you. So I'll move on to topic now. So I'm going to be talking about equilibrium allele frequency in terms of invasion and fixation conditions. And so there's basically two concepts to understand, which is the equilibrium allele frequency and then the invasion and fixation conditions. So by way of introduction, I'm going to start with a basic population genetic model. So just go back to, introductory population genetics. So probably kind of a revision for lots of you, but hopefully it'll make sure everyone gets on the same page and, we'll understand what we're talking about. And yeah, my goal anyway is for you to learn something new about something old. So we'll start with this introduction. So our basic model is that we have I should say, please interrupt me at any time. I can't see anyone or anything, so just flag up to me. I'm happy to have questions at any point. So it's a one locus model with two alleles. We have selection on diploids. And the notation is that you have big A alleles, little a alleles, and the frequency of the big A is P. And then these things have different, the adults have different survival fecundities, which are given by big W's. Yeah, that's called fitness. And so what we're interested in is the change in allele frequency, which is called delta P. And I'm using this thing where you highlight the different terms to explain it, but the colors will change. So yeah, so this one is the big A adults, and they have fitness W big A, and they're all going to produce new big A alleles. And then these are the heterozygotes. And then you have this term of O2 because only half of the gametes they produce will be big A and the other half will be little a. So these two cancel. And then on the bottom of the fraction is just all of the new gametes produced of big A or little a. So that means this is this whole fraction is a new frequency of big A alleles, and this is the current frequency. So that is obviously giving you your allele frequency change. So now I'm just going to plot delta P. So this is a plot of delta P for these different fitness values, for example. And here, if you're at a low initial allele frequency, so the darker colors, the allele frequency change is positive. So if you plot through time, then allele frequency is increasing through time and reaching this midpoint here. And then, yeah, so the colors here in the starting frequencies, as you can see. And then if you start from a high initial big A allele frequency, then the change is negative. So you go down from a high point towards this intermediate equilibrium. So the point you reach is here in the middle, and that's called the that's the equilibrium frequency that we're interested in, and we're calling that P hat. By convention, and obviously in this case you can calculate what that is. Yeah, so this we're basically interested in this case in what's called balancing selection. So that means you're reaching an equilibrium which is somewhere in the middle. You can imagine with different choices of these parameters, this is positive for the whole length, and the allele frequency just goes to 1, or negative, and the allele frequency just goes to near 0. But we're only interested in cases where you end up somewhere in the middle. and you reach this p hat equilibrium allele frequency. And just a quick note on that, on like a per locus or per mutation basis, this type of arrangement might be considered rare, but they have like an outsized influence because you reach an allele frequency somewhere near 0.5, which is where there's maximum genetic variation. So that can be important for, you know, subsequent evolution, or maybe like modifier models of the type that Denis mentioned earlier. So, you know, even if this is, so balancing selection is of interest because it maintains more genetic variation than, say, mutation selection balance, where you hover around near zero. Even if it might, yeah. So we're only talking about balancing selection, and this is the equilibrium allele frequency, which you're probably familiar with. So our other concept was the invasion conditions. So, you're here, we're starting from when you have no big A alleles, which is when P is near zero. We're interested in if you have a perturbation, do you then increase in frequency from zero? So it could be a new mutation or a migrant or something. So this is just a stability analysis around this zero equilibrium. And in this case, it's just one dimension. So it's just see the derivative. So this is a zoom in of this portion of the pot. And what you need for this to be unstable is that on the right of here, this needs to be positive, so that then you're increasing in frequency away from zero. And for that to be true, this slope basically has to be positive in this one-dimensional case. And that condition for this slope to be positive is given by this term here, which I'm calling I0, so the instability at p equals zero. And yeah, just a brief note, this isn't the derivative, this is the part that determines the sign. Yeah. So if this is true, then the slope is positive and you've got invasion. So it means if you introduce a few big A alleles, you move away from zero and you end up maybe somewhere in the middle. Obviously, the other thing you need is that you don't just invade, but you don't fix. So you need invasion and non-fixation to get balancing selection. And so in this case, we look at the other end. So you're introducing a few little A alleles, and then the number of little A alleles has to increase, which means the number of big A alleles has to decrease. So this slope has to be again positive, so that you get negative change here. And the condition is similar. And again, this is the thing that determines the sign. And I'm calling that I1, so instability of the P equals 1 equilibrium. Okay, so just a bit of revision there, but yeah, so there's our three concepts. We've got invasion, non-fixation conditions, I0 and I1, and then the equilibrium P hat in the middle. And then the observation of interest is that P hat is just equal to invasion over the invasion condition, I0, over the invasion condition plus the non-fixation condition. So quite convenient form. For example, you know, in your introductory population genetics class, you're only interested in P hat when it's frequency, so you're only interested in it when it's between 0 and 1. And so you might be asked to, say, prove that this is between 0 and 1, but you can see that immediately from this form, that requires that both these things are positive, or that these things both have the same sign. So if these are both positive, then this immediately exists between 0 and 1. So that's convenient. The other possibility is they could both be negative, in which case this is basically a repeller. But we're only interested in when it's a tractor like this for now. So yeah, so it's kind of a convenient form, and you know, maybe useful for some further analysis, and it's concise. But it's only of like limited interest in as applied to only this one model. But here's my. So I don't know if that's been, you know, described in so many words, but my observation, you know, our motivation today is this. So this same type of relationship is like true for many different models that people are interested in, you know, with biological complexity and have studied. So this is like my most important slide because it motivates what we're going to do. So we'll spend a few minutes talking about this. So this is our relationship of interest, that you're writing the equilibrium in terms of a simple combination of the invasion and fixation conditions. And then I said that this holds true under a number of models that biologists are interested in. So imprinting, this means that the effect of an allele depends on which parent it was inherited on. So maybe for the mother or father, it will have a different fitness or effect on the phenotype than when it's inherited from the, when it's inherited from the father, it has a different effect from when it's inherited from the mother. And then meiotic drive is to do with transmission. So it means that instead of producing heterozygotes producing 50-50 frequency of the two different alleles, they have some bias, like a selfish genetic element. That means you get an overrepresentation of big A or little a. And it might occur by killing all the little a's, say. So you only have big A alleles. So you actually end up with less sperm. And so that brings me on to the next thing, which is competition among the sperm. So they can, sperm from multiple males can compete depending on how many males are mated with by a female, and they might have their haploid or their diploid fitness during sperm competition. Right, and so this brings on to the mating systems. So this is like who's mating with who. So selfing has been mentioned already in this workshop, which is when you are a hermaphrodite and the male, some of the sort of eggs from the same individual are fertilized by sort of sperm from that same individual, and some are fertilized by different individuals, and or they can reproduce asexually, or you can monandry or polyandry is like how many males you're mating with. So the point is that these all interact, and even with all the different interactions, which are like interesting and not like trivial, this kind of relationship between equilibrium allele frequency and the invasion fitness is still holds. And so I only showed you like a one variable example, but I've talked a lot about separate sexes. So you need two variables. You have a frequency in the males and a frequency in the females, and so this holds in the case of X linked. So that's like females are XX and males are XY alleles. So we're going to talk about this in a bit more detail, and also separate sexes. So you have a frequency in the males and frequency in the females, and they're like autosomal. And so this is like a non-comprehensive list that's like biased towards my like previous experience, but I did check. So if you have two patches with like migration between them, which is kind of analogous to separate sexes in some ways, then if there's like weak selection, which is a common assumption to calculate this equilibrium, then you still have this relationship. So I've gone into quite a lot of belabored this point a bit, but basically there's like a lot of models, and I don't want to say that these models are equivalent to one another. For example, you can't just say incorporate meiotic drive into one of those fitness terms we have earlier. They're not equivalent models, and they're not like they can get quite complex, but this relationship between the invasion and the invasion and non-fixation conditions and the equilibrium frequency still holds. So our question is like, what is it that's linking all these different models? What is required for this to be true, and like when will it not be true? So and so in so many words, we're just going to try and determine. I don't think. Yeah, so I should also mention, I don't think this has been pointed out before, but as far as I know, I've asked a few others as well, and we want to know what is it that's kind of like the common feature of all those different models. Okay. So to do that, I tried to sort of abstract and generalize a little bit more. So here we're still going to just quickly do a one variable case. So you only have a change in allele frequency, and the f of p is just a function that means new big A alleles, and g of p means new little a alleles. So it has kind of the same form but more generalized. So we want to know like what has to be true about f of p and g of p for the the relationship of interest to hold. So firstly, our invasion and non-fixation conditions. So for big A to invade, that's our I0, you need this F prime 0 minus G0, which is basically just new big A alleles when big A is rare, has got to be more than the new little A alleles when big A is rare. So, you know, it makes sense, which is nice, but it's also kind of like obvious, which is what often you get when you abstract things a little bit. Okay, and so then here's our thing of interest, so that we know what is, yeah, so there's obviously equivalent to this for I1. And this is our relationship of interest. And what I'm saying is that this is true if you have this assumption, linear assumption about marginal fitness. So marginal fitness is like f of p over p. It's called marginal fitness, and it has to be this like linear combination of your marginal fitness when you're rare and your marginal fitness when you're common. So in the example we showed, these are just constants, but they can be a bit more complicated than that. But you know, this is true for like more complicated models, and I think the reason is of these common assumptions. So firstly, the fitnesses themselves, like how strong is my optic drive or whatever, are not themselves necessarily frequency dependent. They're only frequency dependent comes from the changing frequency of different genotypes. You know, and how often you're meeting with this person and so on. So yeah, obviously if you had some, I think if you had some explicit reason why this thing changes when it becomes more common, aside from its interaction with different types of genotypes, then I don't think this would hold. And also there's a normal assumption of what's called random mating, which means basically that there's the proportion which matings occur are in proportion to the genotypes. So you know, the frequency of big A among some male gametes, and then the frequency of big A among female gametes, that's going to give you your frequency of big A's. So it's kind of uniform random, if you like. Okay, so that's basically the answer of like, I think what's linking all the different models, but I'm going to go into a bit more detail outside the like one dimensional case, because I think it gives us a bit more interesting intuition. So start with this thing I mentioned of X-linked. So females have 2 X chromosomes and males have 1. And that means, so for an allele that's on there, if you're in a male, you inherited your X from your mother, and you can only then transmit it to a daughter. You've got slightly sort of like asymmetric transmission system, which is what makes it interesting. So I've sort of done analogs of those equations. So things that are in green are kind of like things that happen in females, and things that are in purple, things that kind of happen in males. So the female's frequency changes depends on both male and females frequencies, but the male frequency only depends on what was previously in females. So it's kind of a special case. So this is also a haplodiploid. That means like ants and wasps and stuff, where basically the males are haploid. So their whole genome is kind of like one big X chromosome. So these are kind of the same. Okay, so first thing is the invasion conditions, which I think is slightly interesting in this case. So one way of understanding the invasion conditions is to think of, okay, a mutant, say, arrives in female, you know, does it grow between now and the next time it's in a female? So this green line is this term here, which is just its growth rate going back straight back into females. And the alternate way it can get back into females is to go first into a male, which is pink, and then back into the female. And so that together has to be bigger than 1, or so for it to basically be increasing in frequency. So that's one way of thinking about these invasion conditions. And the reason, yeah, so the first one point is that people often say like, oh, an X chromosome is in females twice as often as it's in males. And so female fitness is kind of weighted twice as much. But I think that's basically an approximation of this, where you do a weak selection approximation, basically a Taylor series, and so this multiplication becomes basically an addition, and then you ignore the interaction, so then you end up with two female-ish terms, the orange and the green, and one male term. So I think this is like a more precise way of thinking about X chromosome fitness. This weighting rather than exactly a 2/3 to 1/3. That's just a slight aside. But the main thing is I wanted to point out is by doing this sort of transmission thing, is that we're including all these effects of different parent of origins and things that are happening only in males, you know, and their interaction with females and so on. So that's why we can incorporate all these different complications of interest into the invasion fitness, because we're able to include parent of origin and sex-specific effects. Okay. Okay. So now I'm just going to speed up a little bit, but yeah, the relationship of interest was this p hat is this thing, and the male equilibrium frequency, which I'm calling P2, so P1 of females and P2 males, is the same, but kind of altered by one generation's worth of selection in males. And then, yeah, we have to make basically analogous assumptions about the marginal fitnesses. So being a linear combination of marginal fitness when P1 is rare and when P1 is common. And then there's analogous assumption for little a and also for P2. They're kind of linear. And in this case, because male fitness is only a function of P1, it becomes very, very simple. But yeah, so I think basically it's the same assumption about frequency independence and random mating. Okay, so now maybe more interesting or more general case where you've got like you've got males and females, and all transitions can happen. So male frequency is a function of both male and female frequency. And again, we can understand the transitions in terms of your growth rate between times you're in a female. So you can go straight back into a female in green, or you can go into a male and then straight back into a female, or you can go on in males and then maybe later on come back, and that gives you this term here, which I'm just going to quickly belabor. So this is 1 point, and then you immediately return. That's BC, and then BCD. You skip sort of 2 generations before you get back, and so on, and so you end up with this form here. And you know, as you can probably tell, this is just generic. Like, it's not unique to anything about my models. So it's probably been pointed out before, but my main point is just that you're able to include all these, you know, sex-specific parent of origin effects. So that's why we can link all these different models. And you can think of it this way, which might help intuition a little. Yeah. So in this type of model, you can't just calculate the equilibrium, but you often make this assumption of that selection is weak. So all the sort of allele frequency changes caused by selection are small. And in that case, the equilibrium is the average. So the average across the male and females is given by this term, which is, you know, what I'm trying to point out today. Yeah, and then you also have another term which gives you the difference in frequency between males and females. And yeah, obviously this doesn't have to just be males and females. I mentioned it could be 2 patches with migration among them, or you know, it could be maybe a stage structure population. So there'll be like seeds and adults, and this would be like germination and seed production, and then survival. And they might have different selection pressures. And this would be the average frequency if you assume weak selection. And yeah, weak selection is basically enforcing this assumption that marginal fitness is a linear. Okay. Yeah, so it's a bit more generalizable. So I'm just going to summarize. Sorry, I think yeah, let's just keep going. So yeah, so I think this is like interesting because it's concise and interpretable. So you can just say, oh, it says your equilibrium frequency is like just a simple balance between your advantages when you're rare and your advantages when you're common, or disadvantages when you're common. And it makes sense with those, the required assumptions make sense in terms of, well, you can imagine if fitness is basically frequently independent, then you can imagine that you would end up at some midpoint that just depends on your initial and eventual advantages, just sort of like simply balanced. So it's maybe somehow intuitable. And, you know, I belabored this point that we can include all these different parent of origin effects of interest through these invasion fitnesses. And, you know, could be like a useful shortcut. So we'll just mention that some of the references I mentioned in my motivation slide have these eyes, but they haven't given this. So they kind of got this without knowing. You know, and I guess it's up to you to tell me if it's like useful or interesting. But you know, it's kind of interesting that we can link together these different models, and I just want to point out that this is the form. So yeah, my goal is hopefully you learned something new about something sort of maybe more familiar. So hopefully, and then I've got a few points of discussion. So obviously I've limited this to one locus models. I don't think, you know, this exactly is going to apply in two loci, which is a lot more complicated to calculate the equilibria. But I've also only done 2 alleles and up to 2 variables. But, you know, you kind of think, okay, well, maybe there's some form that looks a bit like this, which is also true for more than 2 variables or more than 2 alleles. So like if you had many patches and weak selection, maybe this would be the average equilibrium frequency among all patches. And then I just want to raise, like, this is like a way of getting us into the idea that it's like generally useful to express our equilibria in terms of the invasion conditions. For example, if you want to do a sensitivity analysis of some parameter that's in these terms, you know, these you can expect all to be positive, so that might help you in some proof that p hat is always increasing with some change. And also like subsequent analysis, like the if you wanted to modify a model or something that is modifying one of selfing or some other thing. So just kind of to say, I mean, I know the previous talk actually did express the equilibrium in terms of invasion conditions, but it's like an entry route to sort of saying that we have like this is like a useful analysis tool that maybe we have in our toolbox for analysis. So I'll just end there and say thank you and encourage you to contact me again. And then also I've worked a little bit on this with Matt, who's currently on leave, so we haven't quite finished it yet. But so yeah, thank you for listening.
Thank you. Other questions?
Hello. Yeah, I'm the speaker from the previous one, actually. So I'm sorry if I didn't understand everything, of course. But at the end, you said what if there are more than 2 pathways, and it made me think that there's a certain notion in linear algebra. It's called the Newman series, where you have 1 minus x, inverse of 1 minus x. If x is a number smaller than 1, you can write it as a series, 1 plus x squared plus x. And this generalizes to matrices, and the interpretation you can give is that it's summing over a lot of different pathways.
Right.
And,
yeah, I think that's probably exactly let's just return
yes,
this thing here. Yeah, because yeah, as I mentioned,
exactly.
This is just a linear. This is the linear stability analysis. This is just any like linear matrix. So it's like not specific to this, but yeah, I'm just trying to say it's like yeah. So definitely someone has figured this out, has noticed that. I just wanted to point out that, you can include all the...
oh, no, I wasn't criticizing at all. I was just saying maybe
yes,
it generalizes too much more to more different types. Like more
yeah, could you repeat for me, please, the name of the...
I think it's Newman series.
Okay, great. Thank you very much.
I'm bad with names, so maybe I got it wrong.
That's perfect. Thank you.
Okay. So you mentioned selfing at some point, but I didn't quite get if the condition remains true with inbreeding in general or not.
Yeah. So like let's just, as a toy, imagine this, and then I think the usual expression is that you would have, with inbreeding, you have this term F for the amount of inbreeding. So the big A adults are like P squared plus F, and this would be like 2P minus P times 1 minus F. And then you have more of these by an amount F as well, something like that. Maybe P times F. Yeah, but the key assumption still holds. So yeah, this thing is still true if you include inbreeding of that type.